Or compound annual growth rates. And finally, I'll help you understand seasonality of data and how to forecast with multiple regression. So roll up your sleeves and let's get ready to learn a lot about forecasting. Next year, you probably want to know whether or not your favorite sports team will win the next game. Some examples of time series. You also see daily coffee sales at a fictitious coffee shop, say Central Perk on The Friends Show. In the next video, we'll learn how to use a time series plot to summarize. In this video, you will learn how to use Excel to plot time series data. If you want to follow along with me, please open the file Yankees Start in the Chapter 1 Video 2 folder. Let's look at what's in this file. For the years 1993 through 2013, we have the number of runs scored by the New York Yankees, column C. Sort of data I do control how to create the scatter charts. Click the drop-down arrow, and we want to do this a line graph without markers. But we could put markers in and we will later. For how many runs the Yankees scored, and the red curve shows us the same value each year, the average number of runs the Yankees scored in a season, 874 runs. In the next video, in this video, we'll discuss another important component of a time series, the trend of a time series. If you want to follow along with me, you should open up the file Trend Start, the Chapter 1 Video 4 folder. Trend is simply the change in level from one period to the next in a time series. So let's look at the 3 time series that we discussed in our last video. Let's look at the number of runs the Yankees scored from 1993 through 2013. There appears to be no real trend, significant trend in the level during those years, 1993 through 2013, so we would say basically no trend. Now let's look at the percentage of Caucasians in the United States during the years 1970 through 2010. And you can see there's a slight downward change in the level each period, and we'll see in a later video that this trend basically is there's a downward trend of 4% a year. Let's now look at the Cisco revenues. You see there's a really steep increase in the level each year. This trend is really a percentage trend. In other words, the change in the level each year is not the same absolute amount, but it turns out it's a percentage amount. And we'll see later, there's really a 70% trend per year in Cisco revenues. In our next video, we'll look at another important aspect of time series, seasonality.
Hello dear, how are you? Please, can you send me the packing list of the shipment that you received? Yeah, please. Thank you.
And you can see there's a rather smooth increase in Amazon's revenues on the moving average trend line. And that lets us better understand the level and trend of Amazon.com revenues. If we didn't have that moving average trend line in the chart, the fact that every fourth quarter is higher than the other 3 quarters would obscure the growth of Amazon, which becomes fairly obvious when we have the moving average trend line inserted in the chart. The insertion of the moving average trend line in the chart enables us to see the smooth growth in Amazon.com's revenues, which was obscured by the fact that every fourth quarter was higher than the other 3. In this video, we're going to look at some forecasts and try to understand why some forecasts are better than other forecasts. So if you want to follow along with me, you should go to the Chapter 2 Video 1 folder and open up the file Accuracy Bias Start. And so what do we see in this file? We see hypothetical sales of a product listed in column D, and then 4 different forecasts for the sales of each of those 6 months are listed in columns E, F, G, and H. And so we want to try and understand which of these forecasts are better than others. And the key concept you've got to start with is the concept of error or residual. These terms are used to mean the same thing in the forecast literature, and I'd say 50% of the time people will use the word residual, 50% of the time people will use the word error, so you need to be familiar with both words. And it's very simple. The error in a forecast, or the residual, is the actual value that occurs minus the forecast. And so let's create the errors for each of these 4 forecasts, and I think it'll be clear to you which of these forecasts are better than others, and that'll lead us into our discussion of accuracy and bias. So we'll have to do a little bit with Excel formulas here, and you'll have to know the copy command. So you'll have to know that when you $sign a, we take the actual, hitting the F4 key, you can see I cycle through my $signs. I hope you nothing, and then we step the 4, and that copies the formula. Okay, so now we see the error for each month for each forecast. So now let's qualitatively look at these errors and try and figure out what's going on. Well, I think you see for forecasts 1 and 2, we're always off by 2 units. And for forecasts 3 and 4, we're always off by 5 units. Forecasts 1 and 2 are more accurate, and we'll make this more precise later in this chapter, than forecasts 3 and 4. And again, that's because we're off by 2 units in forecasts 1 and 2. If we look at forecasts 3 and 4, we see we're always off by 5 units. In this video, we'll discuss a common measure of forecast accuracy, the MAD, or the mean absolute deviation. And so if you want to follow along with me, you should open up the file MAD Start in the Chapter 2 Video 2 folder. So what you see here is basically 6 and you average the absolute, is also you don't just average absolute deviation. Month 1 to months 2 through 6, we could drag the formula down. Let's just do that and show you how that. The left mouse, so you take equals ABS, all Excel formulas start with equals, absolute value of F3. And I could either drag that formula down or I could double click the left mouse. Now to get the MAD, I simply average those absolute errors in column G, and I do that with the average function. So we're off by an average of 10 1/3 units per month in our forecast. Is that good or bad? Well, you have to decide. We're forecasting numbers that are around 30. If we're off by 10, that doesn't seem very good, and we'll make that more precise in the next video. But let's suppose you didn't think of taking the absolute errors and you just average the actual errors. So that's column F. When you average the actual errors, now when I type AVE, I don't have to finish the formula. I can double click here. Excel has autocomplete on formulas, and I get average. If you want to type the whole formula, that's fine. But if I average the error column, no matter what the forecast and the actual numbers, you'll get 0. The positive errors and the negative errors always cancel out if you don't take absolute values. And that's why we had to take absolute values, because otherwise every set of forecasts would look like it was equally good because the average error was 0. If all your errors are 0, your MAD will be 0, and that's your benchmark. Perfect accuracy, but that's really difficult, if not impossible, to obtain. And in our next video, we'll learn about another measure of forecast accuracy called the MAPE, or the mean absolute percentage error. In this video, squared errors often are pretty simple. You simply compute the error for each observation. Error, like in the MAD app forecast, squares 33. And again, if I want to do that for another time series, I could just copy these formulas with Control-C. Copy those formulas down here. You can see here we're always off by 10 units. So each time I square the error, I get a 10 squared or a minus 10 squared, which is 100. And the sum of squared errors would equal 400 in this case. And again, the importance of the sum of squared errors will not become clear to you until you start studying chapter 3. But take my word for it, it really is quite important to understand the concept of sum of squared errors. And again, for all 3 of these measures of forecast accuracy, the MAD, the MAPE, and the sum of squared errors, lower is better, higher is worse. In the next video, we will talk about the concept of forecast bias, which means are our forecasts systematically too high or too low? When you think of the word bias, you probably think of the word prejudice. But in the forecasting world, what does bias mean? Essentially, bias in the forecasting world means your forecasts are either systematically too high or biased. So I said, what do you do? We did 5 folder. Would mean that your forecast, next video, compute the bias for series 1 will take for each observation the actual sales divided by the forecasted, and then we'll subtract 1. And then we'll copy that formula down, and then we'll average those to get our actual value was 11% higher than our forecast on average. Let's do the same for forecast 2. And instead of copying the formula, let's just go ahead and compute it again, since minus 1. And then we'll average those out. Copy that down. And we'll see what the mean bias is here. See, I think clearly what we mean by bias when you average those numbers. Look at all those actual divided by forecast minus 1. They're all negative. What does that mean? The actual sales was less than the forecast in every case. That shouldn't happen. Some of the time, actual sales should be higher than a forecast, and some of the time, actual sales should be lower than a forecast. So I think you can see we have more serious bias in forecast 2 than we have in forecast. If you recall from the last video, the average bias for forecast 1 was 11%. And the 0.36%. So this means we're 95% sure the mean bias for forecast 1 is between minus 15 and 37%. That includes 0, so the bias is not significant. Or we really can't conclude that this bias indicates something that's statistically significantly different from a 0 bias. Let's now do this for forecast 2. We take the mean bias for forecast. You may have heard your boss say our sales are trending up by $10,000 a year. Want to follow along with me? Of Caucasians in the United States for the years 1970. This requires the creation of select our data. We go insert, and then we go to scatter. We'll pick the first choice. So we now have the percentage of Caucasians in the United States each year 1970 through 2010. Now when you plot the data, it may not always look like a straight line will fit the data. Great German mathematician Carl Friedrich Gauss lived in the 19th century. And then we want linear because we think a straight line is averages in chapter 1. To get a trend line, you right click on the points, you go add trend line. And then we want linear because we think a straight line is relevant. We want to select display equation and display R squared. Don't worry about the intercept button there. And then basically we'll find the line that best fits the points and we'll get the equation of the line. So if we look here and we X out of the trend line points, we probably want to make this a little bigger. So if I select this and I do Control 1 to bring up format cells, I can make this, let's say, a 15 point, we'll say 16.5. And the best fitting line here is Y, which is the percentage of Caucasians in the United States, would be minus 0.4 times X, which is the year, plus 875.6. Now, what the R squared means, we'll get to that a little bit later. But in the next video, we'll interpret this trend line and try and explain what it means. Well, that doesn't help us much in this example because X, which is the year, 75.6 Asians in the U.S. %. You put in a 2300 year, this would turn out to be a negative prediction, and I don't think there can be a negative percentage of Caucasians in the United States. And 0.4 times 2030 plus 875.6, and that would give us a prediction in 2030 that 60 caveat relationship that we have fit so well with this line. Now in the next video, we'll learn how to interpret the R squared value on the trend line output, which you've seen in the previous 2 videos, but we haven't really discussed its meaning. In this video, we'll discuss the important. In this video, we'll show you how to create an exponential trend curve and make forecasts based on the trend curve. If you want to follow along with me, you should open up the file expo start, which is in the chapter 4 video 2 folder. Okay, so let's review the data we had for Cisco Systems. We had revenues 1990 through 1999 in millions of dollars, and we realized a linear trend line would not do well. 2.7, let's round it. 1 corresponds to 1990. Year number 2 corresponds to 1991, etc. And for the first time, we do exponential. And we can do the equation in R squared. Our equation is very small, so we'd like to move it and resize it. So first we're going to move it. More discussion of that in a couple of minutes. But let's create the forecast or predictions based on this curve. Okay, so we take 58.553 times EXP is how you raise e to a power if you didn't know that. So we take the power, 0.5694, times the year number. Remember, it's a 1, not a 1990. Run this exponential growth. Copy those predictions down. And those are predictions for each year. And you can see, again, there's a really good fit to the revenues here until year 10. And what you'll find is with new high-tech companies, like Cisco was, exponential growth often fits the data well early on. But you have to beware of extrapolating forward because a lot of times the sales will flatten out after a while and you'll see an S-curve. And fitting S-curves is beyond the scope of this course. But if you look at the last year, 1999, and if you remember, there was a tech recession that started in 2000. NASDAQ was at 5,000 in early 2000 or 1999. And then it dropped severely to 2,500. I hope you didn't buy NASDAQ at 5,000 then. It's still not back there. But basically, the actual sales in 1999 were 12 billion. The prediction was 17.4 billion. So in 1999, Cisco fell well short of the predicted revenues from that company. Guess what? We're in the dotted line. You can see it does a really good job of EXP is okay. So we take 58.553 times EXP is how you raise e to a power if you didn't know that. So we take e power 0.5. When valuing a company, it's important to have a good estimate of how fast the company's revenue is growing. In this video, you'll learn how to use the compound annual growth rate. And it's very simple to use exponential growth to estimate a company's CAGR over a given time. A prediction increases by the same percentage. Take this percentage and subtract 1 and you have the CAGR, or compound annual growth rate. Okay, so this is really simple. So we take the ratio of the predictions. So we start in the second year and we take the ratio of the prediction for the second year to the prediction for the first year. Second year prediction divided by first year prediction, copy that down. And they're all the same because that's the property of exponential growth. When x goes up by 1, the forecast from the equation will go up by the same percentage. So subtract 1. Your CAGR for Cisco in the 1990s is 77%. CAGR, this video, if you projected out that growth rate, but in 5 or 6 years, Cisco would be a $500 billion company. And that just, and I would challenge you, 30% big as a company, where are you going to find the growth? You can't grow your annual growth rate during its early years. That will keep up that growth rate forever. It just doesn't happen. And so you need to be wary of extrapolating exponential growth far beyond the range of data that you have. In our next video, we'll give you a challenge. The fourth quarter of the year is the months October through December. As you probably know, and we pointed out in the Chapter 1 videos, Amazon.com sells a lot more merchandise during the fourth quarter than any other quarter, primarily because of the holiday season. This is an example of seasonality. And the problem with seasonality is it makes it really difficult in the remaining 2 chapters used by many corporations. Therefore, this company tends to sell 30% more than an average quarter. That's what the 1.3 means. And in Q1, this company sells 20% less than an average quarter. That's what the 0.8 means. So seasonal indices must have a certain property. They must average to 1. In other words, the quarters that are above average must sort of be canceled out by the quarters that are below average. But you really can't do much forecasting on quarterly data or monthly data if you don't understand seasonality. And that's going to be the main topic of this entire chapter. But in this video, we just want to give you a simple understanding of seasonal indices. So we have a little brain teaser for you that I use often when I train at companies. Fourth quarter is great. Its seasonal index is 2. So what does that mean? Sales tend to be half of it, 15. They solve real problems. Well, you're not a very good consultant if you think that, because you're neglecting seasonality. What you have to do is really deseasonalize the sales. I often say desalinization, but deseasonalize. So what you want to do is say, hey, what really happened in each quarter in terms of an average quarter? Basically Q4 of 2014, but the seasonal index was 2. So that's really like selling this much in an average quarter. You divide by the seasonal index. That's a pretty good estimate of what the level was during that Q4. In other words, 400 in Q4 is basically telling you the level of the time series based on that observation was 200 in that fourth quarter. Now, when you deseasonalize Q1 of 2015, you divide by the seasonal index for that quarter of 0.5 and you get 400 in an average quarter. So if you look at this the right way, even though sales dropped 50%, the data indicates that the level of sales doubled from Q4 15. So you can see from this very simple example, if you didn't understand seasonality, you would draw an incorrect conclusion that this company is doing worse when they're actually doing fantastic. So in the next video, we'll introduce the ratio to moving average method, which can be used to incorporate seasonality and forecast and estimate. In this video, we'll put everything together and create forecasts for year 6. Recall we have 5 years of data, so we're trying to forecast the next year of sales quarterly. And we had 10 years of data, we would forecast year 11. So here's the process. We use the trend line, slope, and intercept to predict the level of the series during each quarter of the next year. So we'll take that intercept and slope, we'll put in x equals 21, x equals 22, x equals 23, and x equals 24 in the slope. That gives us a prediction for the level of the series. And then we'll look up the seasonal index and adjust the level by the seasonal index. For instance, if the seasonal index was 2, you would double the level to get your final forecast. If the seasonal index was 0.5, you would multiply the level by 0.5 to get your final forecast. So let's show you how to do this. And we used a little trick here that you may not know called range names. In other words, I named the intercept with the word intercept and the slope with the name slope. So if you click on slope in the name box, it takes you to that cell which has been named slope. And we'll show you how to name that in a second. You click on intercept, it goes to this cell which we named intercept. So how are those names created? Well, there are several ways, but the easiest way is just select the names and what you want to name right here. And you go formulas, create from selection, names in left column. So what that does, it takes the left column of the range you selected and associates those names with the cells in the right column. So the word slope now means F1 and the word intercept now means F2. And so when I point to those cells, you'll see the word slope and you'll see the word intercept. That's a nice trick. Okay, so let's compute the level. We take that intercept, we point to it, plus we'll take the slope. Notice our formulas are showing up in plain English, which is really sweet. And then we multiply by the quarter number, which is 21 here, and we copy it down, it'll be 22. Oh, when you name something, it's like it's dollar signs. You don't have to worry when you copy this that you had to dollar sign the intercept cell or the slope cell. So we copy this down and we see the levels going up about 7 per quarter. And that's because our trend was 6.94. Okay, well, that's not the final forecast. If you think that's the final forecast, you should report you really haven't learned much from the previous videos. We need to layer on seasonality. So quarter 21 is the first quarter. You need to look up the first quarter seasonality, and those will come from column L here. When quarter 22 is the second quarter, you look up the second quarter of seasonality. So what we want to do is adjust the trend line level by the seasonal index for each quarter. So we need to look up the seasonal index in this yellow column, and we're going to use a vertical lookup function. And what we're going to do is name the lookup range so we don't have to dollar sign it. So we can select these 3 columns, and if we go to the name box, we could type the name season and hit enter. It was already in there, but if you hit season and hit enter, that would have created the name. So if you select a range and you type the name of the range in the name box and hit enter, you've created that range. So when you click on season, you'll see those 3 columns, which will be used in the vertical lookup. Okay, so what we want to do is adjust the trend line level by the seasonal index. In other words, if the seasonal index was 2, we would double the forecast from the trend line, etc. So we take that trend line level, then we multiply by a vertical lookup, which means you want to look up the quarter of the year, which comes from column D, and then you want to go to the range for the lookup, which we've named season, so you don't have to dollar sign it because it'll be automatically dollar signed by the act of naming it. And then from the third column is where you want to find your answer for the seasonality. And then if you copy that down, that will create your forecast for each quarter. So to recap what we did here, because it's fairly complex, we used the trend line to create the level for each quarter, just sort of increasing the level by the slope each quarter. And then we looked up the seasonal index and multiplied that by the trend line level to get our forecast for quarters 21 through 24. And that really completes the exposition of the ratio to moving average method that you'll find in most textbooks. But I want to add a little wrinkle to this, because the problem with the real world is the trend doesn't know it's supposed to stay constant. The trend changes over time. If you don't believe that, look at housing starts in Southern California. From 2000, the trend doesn't know it's supposed to stay constant. The trend changes over time. If you don't believe that, look at housing starts in Southern California. From 2000 through 2007, housing starts were going gangbusters. There was a really strong positive trend in housing starts. Starting in 2007 or 2008, I'm not sure exactly when, there was a negative trend in housing starts. In this video, we'll show you how to modify the ratio to moving average method to create forecasts using a more recent estimate of trend. Because as we mentioned in the previous video, trend is constantly changing. And so using a more recent trend may give you better forecasts for future quarters or months. Okay, so how are we gonna make this work? Well, we're gonna estimate a trend based on recent data, so we'll just pick the last year. So basically I can take the last 4 periods of centered moving average, which we have right here, and I can fit a trend line slope to that using the slope function. Use a different color there. In other words, if I want to predict the orange from the blue, I can use the slope function to get an estimate of the more recent trend that's based on our last 4 quarters of centered moving average. So I can do that using slope. Y comes first, that's the centered moving average. X comes second, that's the quarter number. And so we get a slope of 8.15. Recall from the previous video, the slope for the whole time frame was 7. So it looks like the trend is speeding up a little bit recently, which is good for our business. So now I can get the level with the new trend for quarters 21 through 24 if I can get a starting point and just add 8.15, the more recent trend per quarter. So what could I use as a starting point for where we are on level in quarter 20? Well, what I could do is take the actual quarter 20 sales and deseasonalize it. So you look at quarter 20, we sold 192. In the fourth quarter seasonality, quarter 20 is the fourth quarter, was 1.19. So if you recall our discussion of seasonality in the first video of this chapter, we could divide the actual sales divided by the seasonal index to get an estimate of level during quarter 20. We have no centered moving average to use. I wish we did. Okay, so we get an estimate there of 161.16. So basically I have an estimate of the quarter 20 level of 161.16. And then basically what I would like to do is basically update that each quarter by the trend. Well, that's simple. I take that estimate of level, I $sign it. I don't want that to change when I copy it down. So I $sign both the letter and the number. And then I take the trend per quarter, and then I multiply it by how many quarters ahead I'm going. And I put in 1 through 4 because that's last video. We would take the level with the new trend and look up the seasonality to get our forecast for the next 4 quarters, which will be higher than our previous forecast because our trend estimate is higher. Up till now, we've looked at extrapolation forecasting methods. So what does that mean? I've never used a term. Extrapolation. Use past data in a time series to estimate what comes next. And there's nothing wrong with that, but it doesn't really give you any insights into what's causing what's happening to the time series. And so in this video, sales and less housing sales, 2 through XN. What are some other independent variables I could use to predict quarterly auto sales? You might want to third quarter of the year. Why? That we've been talking about a lot here. So why is it called multiple linear regression? Okay, it's called linear because this equation is linear. Notice we don't square any of the independent variables. That's beyond the scope of our class here. But basically, if you had an x1 squared or an x1 times an x2 or an e to the x1 or a sine of x1, that would make it not a linear regression. And it's multiple because there's more than one independent variable. And it's a regression because in this video, we'll explain how you can prepare data in preparation for running a multiple linear regression. If you want to follow along, you should open the file Preparing Start from the Chapter 6 Exercise 2 folder. So what data do we have here? If you focus on columns A through the power for called lagging, very common thing. I lag, but for independent variable because Q1, you can say if quarter number equals 2, put a 1 in this column, otherwise a 0, and copy that down. You should see a 1 whenever it's Q2 and a 0 otherwise. So this row 12 is a Q2, you see a 1. Row 13 is a Q3, not a Q2, you see a 0. Now we do the same thing for Q3. We say if the quarter number is 3, put a 1, otherwise a 0. Double click and copy that down. I love that double click trick. And so whenever it's a third quarter, you see a 1. Whenever it's not a third quarter, you see a 0. So now I hope you see why we don't need Q4. 1 and code the other ones using if statements. Now I can create the lag gross quarter. The unemployment rate is what it was last. To the bottom of the is last quarter's GNP. So I say equals D11 going up 1 row. Copy that across, I get lagged unemployment rate and interest rate. Okay, now to copy that down, I can use the double click trick on multiple columns. We haven't had to do that yet. But if I select these 3 columns and get the cross here, and I double click the left mouse, wow, I've copied down those 3 columns to the bottom of the spreadsheet. And you can check every quarter the GNP lagged is whatever it was last quarter. And that would be any progression is to, but I might go back a week later and find out it's not there. And so you would look under File Options, Add-ins, and you would see it's there and you get really confused. So if it disappears, what do? Uncheck it, because it'll probably be checked because you didn't do anything to get rid of it. Uncheck the add-in and reinstall it. This always works, and don't ask me why, because I have no clue. But it's never failed me, but often on my machine, the data analysis add-in will disappear. I'll bet when I go. In this video, we'll discuss how you can determine how well your multiple regression equation fits the data, and also how you're not going to 1,000 in predicting how much money that column. I got 2.4 million. Error is going to be an outlier. So we double that standard.